This is an audio recording for visually impaired students from the book Pardeep's Inorganic Chemistry, Volume 2 by Dr. K.K. Bhasin. Chemistry of Actinides. Actinides constitute a series of elements following actinium in the seventh period of the periodic table. Actinides belong to F block as these are formed by the gradual filling of 5F subcell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides, which follow lanthanum, involve the gradual filling of 4F subcell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. This series of 14 elements is called actinides. Actinides along with lanthanides constitute complete F block elements. The ending IDE in actinides is not appropriate because it more correctly means negative ion, such as oxide or chloride. Actinides were also named as actinones by a group of scientists. However, the ending ON is used preferably for non-metals such as boron, silicon, etc., whereas all the actinides are distinctly metallic. IUPAC has now recommended these elements to be called actinoids with the ending OID rather than being called actinides or actinones. However, it is unfortunate that people still call these elements by their earlier name as actinides. Before World War II, the only naturally occurring actinides, namely thorium, protactinium and uranium, were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reactions. These elements are named man-made or synthetic elements. Another name coined for these elements is transuranic elements. Transuranic elements are elements that have atomic number greater than 92. Let us now discuss the interesting aspects of the chemistry of actinides. Position of actinides in the periodic table. Inspection of periodic table reveals the electronic configuration of noble gas radon as Xe 6s2 4f14 5d10 6p6. After radon, the 7s and 7p orbitals gain in stability relative to 5f orbital because S and P are more penetrating than the D and F block, D and F orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new elements, francium and radium, belonging to S block of elements. After the addition of two electrons in the radon core, the 5f and 6d electrons penetrate the 7s orbital. The least penetrating f orbitals are stabilized and on account of the increase in effective nuclear charge outside the next noble gas core with increasing atomic number. As a result, the next 14 electrons from thorium to lawrencium enter the 5f cell. It is important to note that around actinium, both the 5f and 6d subshell possess almost similar energies. Because of similar energies of 5f and 6d subshell, the incoming electron may enter either of the two subshells, which result in the uncertainty of the electronic configuration. As a result, it is doubtful whether the electron enters the 5f orbital or not. For example, the configuration of thorium may be written as either 5f0 6d2 7s2 or 5f1 6d1 7s2. However, once filling starts in f orbital, the 5f subshell becomes more and more stable. As a result, from uranium onward, the 5f shell becomes most stable as shown in figure 5.1. Thus, all the incoming electrons start filling progressively in f orbital. The general electronic configuration of actinides can be assigned Rn 5f 0 to 14 6d 0 to 1 7s2. General characteristics of actinides. Some of the general characteristics of actinides are detailed below. First, electronic configuration. As already discussed in section 5.1, the actinides involve the gradual filling of 5f subshell. The electronic configuration of the titled actinium Z is equal to 86 is Rn 61 7s2. Thus, from thorium onward, the 5f subshell starts progressively filled. The general electronic configuration of the atoms of the actinides in the ground state may be written as Rn 5f 1 to 14, 60, 0 to 1, 7s2. The detailed electronic configuration of all the elements are presented in table 5.1. Second, physical properties. Some of the physical properties of the actinides are presented in table 5.2, which are discussed below. Melting and boiling points. The melting and boiling points of actinides are moderately high but are lower than those of the transition elements. An inspection of the table 5.2 reveals that there is no regular trend in the melting and boiling points of the non-actinides. Third, density. An inspection of the table 5.2 reveals that the elements near uranium have very high densities. Americium resembles the corresponding lanthanide, europium, in being less dense than its neighbors. Fourth, ionic radii and actinide contraction. The size of the actinide ion decreases regularly along the actinide series. This is because with increasing atomic number, the extra charge on the nucleus is poorly screened by the f electrons. The steady decrease in ionic radii with the increase in atomic number is called actinide contraction. A comparison of M3 positive ionic radii of actinides with those of the lanthanides reveal that the actinides and lanthanide ions are very similar in size. As a result, their chemical properties are also similar. The decrease in the ionic radii of M3 positive and M4 positive ions in case of actinides is shown in figure 5.2. It is interesting to note that there is a decrease in the atomic radii from thorium to uranium, which may be due to the increase in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from thorium to uranium may be considered to consist of Mn positive ions with a total of Ne electrons for atoms. After plutonium, the metallic radius increases significantly again, which may reflect the increasingly lanthanide-like behavior of the later actinides, in which the preferred oxidation state is +3 with only 3 electrons per atom available for metallic bonding. Fifth, oxidation states. The actinide elements show a greater range of oxidation states than the lanthanides, particularly in the early part of the series. The different oxidation states of actinide elements are shown in the table 5.3. Volnos are most common oxidation states. The oxidation states shown in parentheses are unstable. The +2 oxidation state in case of actinides is very rare. Am2 positive has the electronic configuration 5f7. It is the analog of Eu2 positive in the lanthanides but exists only in the solid state as the fluoride AmF2. On the other hand, CF2 positive, ES2 positive, FM2 positive, MD2 positive and NO2 positive exist as ions in solution. The properties of divalent actinides resembles more closely to Ba2 positive in group 2. The most stable +2 oxidation state is exhibited by nobelium as NO2 positive and corresponds to stable 5F14 arrangement. The +3 oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinides. The first 4 elements TH, Pa, U and M, Np do not show +3 oxidation state as the most stable oxidation state. For example, U3 positive is readily oxidized in air as well as in solution. Interestingly, the most stable oxidation state of elements up to uranium is the only involving all the valence electrons. Thus, the most stable oxidation states of TH, Pa and U are +4, +5 and +6 respectively. Although Neptunium shows the oxidation state +7 by involving all its valence electrons, it is not the most stable state. This is because Np in +7 oxidation state is highly oxidizing and most stable state is +5. The +4 oxidation state is exhibited by all the elements from TH to CF. However, Pa and Mp display the most important plus for oxidation state. The M4 positive ions are known in the acid solution and are precipitated by F, PO4 3 negative and IO3 negative ions. The elements all form dioxide MO2 and fluorides M4, MF4. The plus 5 oxidation state is exhibited by all the elements from Pa to Am. However, plus 5 oxidation state is more stable from Pa and Np. It is important to note that M5 positive ions do not occur in solution as such. In fact, these states occur as their oxocations such as MO2 positive ions. A few solid compounds are known, whereas in solutions these ions disproportionate rapidly. The plus 6 oxidation state is exhibited by lower actinides, example U, Np, Pu and Am, in the form of their fluorides. The plus 6 oxidation state is more commonly found as the dioxo ions, that is MO2 2 positive. The ion MO2 2 positive is linear and exists both in the solid as well as in solution. One of the most commonly encountered compounds of uranium in plus 6 oxidation state is uranyl nitrate dihydrate, UO2 NO3 twice dot 2 H2O. It consists of linear UO2 plus ion surrounded by two NO3 negative ions and water molecules as shown in figure 5.3. The NO3 negative groups are bidentate and therefore two oxygen from each NO3 negative are bonded to uranium. Oxygen atom from the two water molecules also bond to uranium. Thus the coordination number around uranium is 8. The UO2 2 positive unit in the compound UO2 NO3 twice H2O twice is perpendicular to a hexagon of 6 oxygen atoms, 4 from bidentate NO3 negative group and 2 from water molecules. The lower oxidation states are ionic, while the higher oxidation states increasingly covalent. The plus 7 oxidation state is known only in the oxocations of Np and Pu when alkaline solutions are oxidized by O3. The important oxo anions known in case of Np and Pu are NpO4 OH twice whole 3 negative and PuO6 3 negative. Sixth, color of the ions. Actinides ions are mostly colored. The color of a particular actinide ion depends upon the number of electrons present in the 5f orbital. The color of the actinide ion arises mainly due to FF transition. The color of the characteristic cation formed by the actinide ion M3 positive, M4 positive, MO2 positive and MO2 2 positive in aqueous solution are given in table 5.4. In addition to FF transitions in actinides, the color can also arise due to FD transition as well as charge transfer transition. The color of the actinide ion solution because of FF transition occur in the visible and ultraviolet regions. We have already encountered this FF type of transition in case of lanthanides as well. Since the 5f electrons in case of actinides are projected out more in space than the 4f electrons in lanthanides, these 5f electrons are strongly influenced by the ligand field of ligands. This makes the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanides. A complex spectra is always different to characterize easily. It has been experimentally found that the absorption due to FF transition in case of actinides are nearly 10 times stronger and 2 times broader than the FF transitions of lanthanide ions. The energy difference between 5f and 6d orbitals in case of actinides being smaller than 4f and 5d orbitals in case of lanthanides, the actinide ion invariably absorbs light of lower frequency or higher wavelength. As a result, the allowed and very strong FD transition lie in the ultraviolet region and therefore do not influence the color of the actinide ion. It has been observed that the actinide ion in higher oxidation state display predominantly charge transfer spectra. This spectra is exhibited only by high oxidation state ions which can easily oxidize the ligands. It is important to note that lanthanides do not exhibit charge transfer spectra because lanthanides do not display oxidation states higher than 4. Seventh, magnetic properties. The actinides show similar magnetic properties to lanthanides in terms of magnetic moments with the number of unpaired electrons. This is shown clearly in the figure 5.4 where the magnetic moment in Bm are plotted against the number of unpaired electrons. It is important to note that the high valence state have been chosen for 5f1, 5f2, 5f3 and 5f4 ions which show the close similarities. Magnetic moment values for the isoelectronic actinide ion are lower than the lanthanide ion, example Np6 and Ce3, Np5 and Pr3, Np4 and Nd3. This is due to the fact that 5f electron in actinides are projected more in space to the crystal field. As a result, the partial quenching of orbitals occur by the crystal field effects. Eighth, reactivity. The actinides are highly reactive metals. These react with dihydrogen and form non-stoichiometric hydrides with the formula MH2 or MH3. They react with hot water and tarnish in air, forming an oxide coating. The actinides react readily with HCl, but reactions with other acid is slower than expected. The metals are basic and do not react with the sodium hydroxide. The actinides react directly with the halogens to form a variety of halides. The redox potential for the M3 positive or M couples are about minus 1.9 volt. Thorium and uranium chemistry has been exploited in detail. Some of the general methods for preparing compounds of actinides are given below in figure 5.5. Occurrence and isolation of actinides. All the elements beyond actinium in the periodic table are radioactive. As a result, the nuclei of all the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is the heaviest naturally occurring element with an abundance of 2.4 ppm in the Earth's crust and is more abundant than Ag and Hg. Among the actinides, Th and U occur on the Earth because the isotopes of U and Th and Pu have half-lives sufficiently long in view of the fact that the Earth was formed several million years ago. Uranium. Since uranium is the most important of all the actinides, its chemistry will be discussed in more detail. The primary natural source of uranium is pitchblende or uraninite, which has the empirical formula U3O2. It is a mixed oxide containing uranium both in 4th and 6th oxidation state as UO2 in 4.2 UO3 6 in the 6th state. The other important ores are carnotite, autunite, calcium carbonate. Extraction of uranium. As a result, as already mentioned, the main source of uranium is pitchblende. The details of the extraction of uranium involves the following steps. First, concentration. The ore is crushed to a fine powder and subjected to conventional gravity separation to remove the lighter impurities. Second, roasting. The concentrated ore is roasted on the hearth of a reverberatory furnace in the presence of air to remove the volatile impurities such as sulfur, arsenic and antimony. Third, acid treatment. The roasted ore is treated with the dilute H2SO4 in the presence of an oxidizing agent such as MnO2 or NaClO3. This treatment converts uranium to a soluble uranyl sulfate UO2SO4. The roasted ore can also be converted to a solution of UO2NO3 twice by dissolving the ore in nitric acid. Fourth, treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution of uranyl sulfate precipitate it has ammonium uranyl carbonate. Alternatively, ammonia is added to the solution of uranyl sulfate obtained in step 3 acid treatment. This gives rise to bright yellow precipitate of ammonium diuranate. This precipitate is often called the yellow cake. This cake on heating give rise to mixed oxide uranium-4 and uranium-6 oxide, that is U3O8 equivalent to UO2 in 2 oxidation state dot to UO3 in 6 oxidation state. Fifth, conversion into uranium dioxide. The mixed uranium oxide U3O8 is reduced to UO2 by heating either with charcoal or with hydrogen. Sixth, production of uranium. Element uranium can be produced from uranium dioxide by using either of two methods. First, UO2 is heated with vapors of HF to form uranium 4 fluoride, which in turn react with magnesium to yield uranium metal. Or second, by converting UO2 to a volatile uranium tetrachloride by heating it with elemental chlorine in the presence of charcoal. This is followed by reduction with elemental sodium. All the steps discussed above can be summarized in the flow sheet diagram for the extraction of uranium. Chemistry of separation of neptunium Np, plutonium Pu and americium Am from uranium. The three elements neptunium, plutonium and americium that follow uranium in the follow actinide series are produced mainly from uranium in the nuclear reactors. If you recall, uranium is the oldest known element amongst the actinides. Naturally occurring uranium contains two main isotopes, that is U92 and U92-238 and U92-235, which occurs in the ratio 99.3% and 0.7% respectively. There is another isotope U92-233 which occurs in traces only. Neptunium and plutonium, named after the planets Neptune and Pluto, were prepared for the first time in 1940 by a team of celebrated scientists by bombarding uranium with neutrons in the cyclotron in Barclay, USA. Both the elements are now obtained from spent uranium fuel elements of nuclear reactor, where they are formed by the capture of neutrons produced in the fission of U92-235 fuel as. Isotopes of plutonium Pu can also be prepared by N2N reaction, in which a fast neutron is added with the subsequent loss of two neutrons with allowing time for the intermediate products to decay. Americium can be obtained from the isotopes of plutonium by the success of N and gamma reaction in the nuclear reactor. The yield of the heavier element after americium is controlled by two factors: the half-lives of the various isotopes and by their ability to absorb neutrons. It is important to note that the stepwise addition of slow neutrons is very difficult. A quick method is used to bombard the nucleus with a large number of fast neutrons without allowing time for the intermediate product to decay. For example, U92-238 adds a fast neutron and then loses two neutrons to form an isotope of neptunium according to the reaction. The separation of these elements from uranium is extremely difficult and hazardous. It is because these elements, including the starting material, are not only highly radioactive but also give highly radioactive fission products. Plutonium especially is extremely toxic. A dose as small as 10 raised to power minus 6 gram may be fatal, while smaller doses are carcinogenic. The separation of Np, Pu and Am from U are based on the following chemistry. First, stability of oxidation states. A steady decrease in the stability of high oxidation state with the increase in atomic number have been observed with the increase in atomic number. The order of stabilities of the major ions involved are Am3 positive, the greater, then Pu3 positive, then Np3 positive and U4 positive. Whereas the order in case of oxo ions are UO2 2 positive, the greater, then NPO2 2 positive, then PuO2 2 positive and MoO2 2 positive, the least. Separation of these elements from uranium, from which they are obtained in the nuclear reactor, from fission product and from one another can thus be achieved by adjusting the solution containing them to a suitable redox potential and then using solvent extraction or precipitation. For example, Pu can be oxidized to PuO2 positive while Am remains as Am3 positive. Thus, plutonium Pu can be removed by solvent extraction, whereas americium can be precipitated as AmF3. Second, extraction into organic solvents. The MO2 positive ions from solutions can be extracted into organic solvents. The M4 positive ions are extracted into tributyl phosphate in kerosene from 6M HNO3 solution, whereas M3 positive ions are extracted from 10 to 16M HNO3. Third, precipitation reaction. Actinides in the +3 and +4 oxidation state can be precipitated as their fluorides or phosphates from acid solutions. The higher oxidation state beyond +4 give either no precipitate or can be prevented from precipitation by complex formation with sulfate ions. Fourth, ion exchange methods. Ion exchange methods are commonly used in separation for small amount of materials, as in the separation of americium Am. Spent uranium fuel rods removed from the nuclear reactors can be used to extract Np and Pu in kilogram quantities, whereas Ame in 100 gram quantities. This processing of nuclear fuel rods is an important technology, as there helps to extract new elements that may be used as nuclear fuel. Spent fuel rods are dipped in ponds of water for several days to allow them to cool. During this dipping period, the intensively radioactive isotopes with short half-lives such as I-151 lose most of their activity. The fuel rods are dissolved in 7MHNO3 and extracted with 30% tributyl phosphate in kerosene. The extraction coefficients of the actinides in 7NHNO3 solution containing 30% tributyl phosphate in kerosene are: the M3 positive ions have very low extraction coefficient in 7NHNO3. As a result, nitrates of UO2 positive and Pu4 positive are preferably extracted in tributyl phosphate, leaving the other actinides, namely Np and Am, along with other fission products in aqueous solution. It is also important to note that 7NHNO3 cannot oxidize Pu4 positive to other oxidation state, Pu5 and Pu6. Reduction of UO2 positive or Pu4 positive or Pu in fourth oxidation state, Pu4 nitrate solution with SO2, NH2OH or FeNH2SO3 whole twice gives aqueous solution of Pu plus 3 without affecting the reduction of UO2 positive. Thus, Pu4 positive is reduced to Pu3 positive, which enters the aqueous phase, while UO2 positive remains unchanged in organic layer. UO2 positive species present in kerosene oil on treatment with 0.2 and HNO3 gives UO2NO3 twice in aqueous solution, which on evaporating leaves a solid mass of composition UO2NO3 twice dot 6H2O. On heating this hydrated solid compound to 400 degrees Celsius gives UO3, which upon further reduction yields UO2. On the other hand, aqueous solution of reduced Pu3 solution on treatment with nitrous acid gets oxidized to Pu4. This solution reacts with oxalic acid to give crystalline precipitates of the composition PuC2O4 whole twice dot 6H2O. Heating the hydrated compound to 300 degrees Celsius gives PuO2. The whole sequence in steps outlined in the process are described in figure 5.6. The separation of other actinides, namely Np and Am, can be achieved by the use of appropriate oxidation reduction cycles coupled with the solvent extraction. For example, Pu3 positive in aqueous nitric acid can be oxidized to PuO2 positive by an oxidizing couple with E0 greater than 1.02 volt, followed by extraction into hexane, whereas Am3 positive is unchanged or remains in aqueous solution. Transuranic elements. Elements with an atomic number greater than 92 are called transuranic elements. Before the Second World War, the elements thorium, protactinium and uranium were located below hafnium, tantalum and tungsten in the periodic table. The synthesis of neptunium, a new element with atomic number 93 by M.C. Millane and Abelson in 1940, was demonstrated by bombarding uranium with nucleus. This newly discovered element should be positioned immediately to the right of tungsten below rhenium. However, the properties of neptunium resembled more the uranium rather than rhenium. It was the discovery of neptunium followed by the subsequent synthesis of new elements that were responsible for the new series of elements called the actinide series. All the transuranic elements are radioactive in nature and have short half-life period. Neptunium, plutonium and americium were unknown prior to their synthetic preparation via nuclear reactions. However, these elements were later found to be present in trace quantities in uranium ores. Synthetic routes to transuranic elements. There are two synthetic routes which are commonly used for the synthesis of transuranic elements. A neutron may be captured by the nucleus with the emission of gamma rays reaction. The neutron increases the mass number of the nucleus by 1 unit and some energy is released as gamma radiation. Further neutrons may be added in a similar way. Addition of neutrons increases the neutron to proton ratio. This makes the nucleus unstable because it contains too many neutrons. As a result, the nuclear decay by converting a neutron into a proton and a beta particle, that is an electron. This reduces the NP ratio and also increases the atomic number by 1. Thus, a new element is formed. The other method involves the capture of small ions by the heavy nucleus. This is possible only if the bombarding particles have sufficient energy to overcome the Coulombic repulsions between the ion and the heavy nucleus. The smaller ions are accelerated in a linear accelerator or cyclotron to possess sufficient kinetic energy. The simplest ion used is the alpha particle, that is a helium nucleus. This increases the atomic mass unit by several units and the atomic number by 2 units. Synthesis of transuranic elements. All the transuranic elements have been prepared by nuclear reaction which involve bombardment of either neutrons, alpha particles or other small nuclei. Preparation of neptunium. It was prepared by M.C. Millane and Abelson in 1940 at Barley, USA by bombarding uranium with slow neutrons when U92 to 239 was obtained. Preparation of plutonium. It was discovered by Seaborg and his co-workers during the beta decay of neptunium-239. Plutonium was named after the name of the planet Pluto. Preparation of americium. Americium was synthesized by bombarding uranium with alpha particles. Preparation of curium. Curium was synthesized by bombarding Pu with alpha particles. Preparation of berkelium. Berkelium was synthesized by Seaborg and his co-workers by bombarding americium-241 with high-speed alpha particles. Preparation of californium. Californium was synthesized by bombarding curium-242 with alpha particles. Preparation of einsteinium. Einsteinium was synthesized by bombarding uranium-238 nucleus with accelerated nitrogen nuclei. 2 isotopes of californium have been identified. It can also be prepared by bombarding isotopes of californium-250 with neutrons. Californium-253 obtained during bombardment process result in beta decay forming einsteinium. Preparation of fermium. Fermium was synthesized by bombarding einsteinium with neutrons as. Preparation of mendelevium. Mendelevium was synthesized by bombarding einsteinium-253 with alpha particles. Preparation of nobelium. Nobelium was synthesized by bombarding curium-246 with accelerated stripped carbon, that is C6 positive. Preparation of lawrencium. Lawrencium was synthesized by bombarding californium-250 with accelerated boron nuclei. A summary of the synthesis transuranic elements along with the half-lives of the element is given in the table 5.5. The later or heavier actinide elements. The elements from the curium onward, namely curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium are named as later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The availability of some of the most accessible isotopes are given in the table 5.6. It is clear from the table that curium is available only in macroscopic quantities, whereas later actinides above atomic number 100 have been prepared only in minute quantities of the order of few atoms. In other words, later actinides are available in tracer amounts. It is interesting to note that the later actinides show close resemblance of lanthanides. However, the actinides can be easily separated from the lanthanides because of actinides readily form complexes. For example, the actinides react with concentrated HCl to form the corresponding chlorocomplexes. If both the groups of ions, that is lanthanides as well as actinides, are observed on the cation exchange column, the actinides can be eluted more conveniently with concentrated HCl. After eluting the actinides can be separated from each other by ion exchange using citrate solution to elute them. It is interesting to note that the order in which the tri-positive actinide ions are eluted show a close similarity to the order in which tri-positive lanthanide ions are eluted. Figure 5.7 displays the elution diagram for the actinide and the lanthanide elements. The first identification of the elements from americium of mendelevium on weightable measurable scale was made through elution. All the actinide with atomic number 96 to 103, that is Cm, Bk, Cf, Es, Fm, Md, No and Lw, with the exception of nobelium, have +3 as the most stable oxidation state. The most stable oxidation state of nobelium is +2. This is because it has most favorable F14 electronic configuration. Actinide with atomic number 98 to 102, that is californium to nobelium, also display +2 oxidation state, except for nobelium. +2 oxidation state is strongly reducing in nature. Higher oxidation states of curium Cm +4 are formed in the solid state in compounds such as CmF4 and RbCmF5. Similarly, berkelium compounds are stable in the +4 oxidation states such as BkO2 and CS2BkCl6. Lawrencium exists only in the +3 oxidation state and resists oxidation and reduction. This resistance to oxidation, that is +4, and reduction, that is +2, illustrates the stability of an F14 electronic configuration. The elements up to atomic number 100 undergo radioactive decay mainly by emitting alpha particle or beta particle. The later element become increasingly unstable as the atomic number increases. Nobelium is extremely unstable and has a half-life of only 3 seconds. Elements beyond Z103. The actinide series is complete at lawrencium Z103. We have already learned that the half-lives of later actinide beyond atomic number 100 decreases considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated that the half-life of the element will decrease further as new elements are discovered. The half-life of an element with an atomic number 108 is expected to be very short, about 10 raised to power -4 to 10 raised to power -6 seconds due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of elements beyond 108. However, these difficulties have not damped the spirit of the scientists, and they have been successful in discovering elements up to atomic number 112. Out of 112 known element up to atomic number 109 have so far been named. A major controversy came to light over naming these elements. The choice of the name of the element belongs to the discoverer. In the case of Actinides, 3 nuclear facilities are in competition for the synthesis of each of the newly discovered element. The facilities are at Berkeley, California, USA, Dubna, Russia, and Darmstadt, Germany. It is extremely difficult to identify which nuclear facility had the true claim. For example, the discovery of element 104 was claimed by both Berkeley, USA, and Dubna, Russia groups. The Americans named the element Rutherfordium after Ernest Rutherford, while the Russians named it Kurchatovium after Igor Kurchatov. While these conflicting claims were being settled, the International Union of Pure and Applied Chemistry (IUPAC) devised a hybrid Latin-Greek numerical system of providing provisional names and symbols to all the newly discovered elements. The names are derived directly from the atomic number using root for 3 digits in the atomic number of the element and adding the ending IUM. The roots for number and their abbreviations are. In some cases, the names are shortened by removing the repetitive letter. Example, bi plus IUM can be written as bium, or tri plus IUM can be written in short form as trium. Let us name an element with atomic number 106 according to hybrid Latin Greek nomenclature. The name of the element is derived by combining together the roots in the order of digits, which makes up the atomic number, followed by adding IUM in the end. 106 is equals to UN plus NIL nil plus hex plus EM, that is unnil hexium. The symbol for the element unnil hexium with atomic number 106 is UNH. Similarly, the name and symbol for the element with atomic number 102 can be worked out. 102 is equals to UN plus nil plus bi plus IUM, that is unnil bium or not unnil bi IUM. The IUPAC names for the elements with atomic number more than 100 are given below. The newly recommended name for the element with atomic number 104 to 109 are also mentioned. No IUPAC name has yet not been announced. Elements not yet discovered. Comparison of actinides and lanthanides. Both lanthanides and actinides constitute elements of F block, as these involve the gradual filling of F orbital. These elements occupy a distinct safe space at the bottom of the periodic table. They show close resemblance in some of their properties but also differ in many properties. Let us review some of the important points of similarities and differences among the lanthanides and the actinides. Points of similarities. First, both the lanthanides and actinides involve the filling of F orbital. Second, both the lanthanides and actinides display predominantly the +3 oxidation state in most of their compounds. Third, due to poor shielding of 4f and 5f electron, both lanthanides and actinides show gradual contraction in the size of their atoms with the increase in the atomic number known as lanthanide and actinide contraction respectively. Fourth element of lanthanides and actinides with the same number of unpaired electrons display similar absorption spectra due to FF transition. Fifth, lanthanides and actinides are highly electropositive and are very reactive. Sixth, nitrates, sulfates and perchlorates of trivalent lanthanides and actinides are soluble in water. Seventh, hydroxide fluorides and carbonates of trivalent lanthanides and actinides are insoluble in water. Eighth, both lanthanides and actinides can be separated by ion exchange method. Points of differences. The important points of differences between the lanthanides and actinides are presented in the table 5.8 below. Metal orbitals. Lanthanides, it involves filling of 4f orbital. Actinides, it involves filling of 5f orbital. Second, energy gap between f and d orbital. Lanthanides, the energy gap between 4f and 5d orbital in lanthanide is very large. As a result, their chemistry is fairly similar. Actinides, the energy gap between 5f60 in actinides is small. As a result, their chemistry is very different. Third, binding energies. In case of lanthanides, binding energies of 4f orbital are higher in lanthanides, whereas binding energies of 5f orbital are lower in actinides. Fourth, oxidation state. The most common oxidation state is +3 in addition to some lanthanides showing +2 and +4. In case of actinides, the common oxidation state is +3 in addition to some actinides showing +2, +4, +5 and +6. Fifth, shielding effect. 4f electron exert greater shielding effect in case of lanthanides and 5f electron exert poor shielding effect in case of actinides. Sixth, ability to form Oxocations. Lanthanides do not form oxocations. Actinides form oxocations in higher oxidation states. Seventh, color of the ions. Most of the lanthanides ions are colorless, whereas most of the actinides ions are colored. For example, U4 positive is green and UO22 positive is yellow. Eighth, complexing ability. The tendency to form complexes is small for lanthanides, whereas the tendency to form complexes is large. They do form complexes with bonding ligands. Ninth, radioactivity. All lanthanides except promethium are not radioactive. All the actinides are radioactive. 10th, coordination number. Lanthanides display coordination number 6, 7, 8 and 9. Actinides display higher coordination number 8, 9 and 12. 11th, basic character. Compounds of lanthanides are less basic in character, whereas compounds of actinides are more basic in character. Thank you.